This is example 10-3, pump with a loss. So we have a little detention pond here, and we're pumping water from that detention pond into the lake up here. So we're asked how much power the pump needs to deliver water at 12,000 liters per minute. All right, what are we going to do? Well, we're going to write the energy equation. Flowing into the pipe, through the pump, over the hump, and into the lake. And we're going to write it from the surface of the detention pond up to where the pipe ends up here. So we can say we go from A to B. So we'll use our energy equation. Where we have PA over gamma plus VA squared over 2G plus ZA plus H pump is equal to PB over gamma plus VB squared over 2G plus ZB plus H turbine plus H loss. Just about fits in there. And now, just like we've done in other examples, to go through and find out what all these terms are. So we can start with a datum. So we have two options, right? We can do it at B or at A. Let's do it at A. Datum at point A, which means ZA is equal to 0 and ZB is equal to 20 meters. We have no turbine, which means that H turbine is equal to 0. We know that both points A, right? So we start somewhere here and somewhere there. So points A and B are in contact with the atmosphere. Which of course means that PA is equal to PB is equal to 0. Also know that point A, point A at the surface of reservoir, which means it is going to move much slower than the water in the pipe there. So we'll say VA equal to 0. So let's see, what do we have? These are the fast, easy ones, right? So we have PA, we have VA, we have ZA, H pump we're looking for, we have PB, so we're missing VB, but we're given the flow in the hose, right? We want the pipe, we want to have 12,000 liters per minute. So of course from that we can get our velocity, but let's convert our Q first, because it's given to us in liters per minute, but we want to have it in cubic meters per second. So that would be 12,000 liters per minute equal to 12,000 liters. Now there's 1 liter. Other way around. 1 cubic meter is what we're looking for now. 1 cubic meter has 1,000 liters. And we started with minutes, so we know that 60 seconds are in 1 minute. Plug that in, we get 0.2 cubic meters per second. All right, so then of course we can find what the velocity is by just saying that V is equal to Q over A. That is the same as 4 times Q over pi d squared. Plug in those numbers. That'd be 4 times 0.2 cubic meters per second divided by pi. Let's see, what's the diameter? 200 millimeters times 0.2 meters squared. That gives me a value of 6.36698 meters per second. And of course, this velocity is going to be constant throughout the pipe because there's no change in diameter in the pipe. However, the velocity is different at A, right? Because we're still at the surface of the reservoir. Velocity will be increasing as we're getting closer to the inlet of the pipe. All right, let's see. We now have, we said we were looking for VB, that we have now. ZB we already know. H turbine we know, so that's left leaving us with the head loss term. And for that, we'll use Darcy-Weisbach. All right, so we want to use Darcy-Weisbach. Darcy-Weisbach. We'll have HL F times L over D times V squared over 2G. That means we have to find what F is. To do that, we need to have the value of the Reynolds number. RE is equal to rho times V times D over mu. Now, are we given the densities? No, but we're given the temperature. 25 degrees C. That's pretty warm water to be sitting in a detention pond. Fish in the river or in the lake are not going to be happy to have that water pumped in. But nonetheless, we can take the 25 degrees C and we can look up what the density is. In this case, it is 997 times 1 kilograms per cubic meters times the velocity that we just calculated, 6.366198 meters per second, and 200 millimeter radius. Divided by mu, again, something we can look up for 25 degrees C in water, 8.97 times 10 to the minus 4 Newton seconds per meter squared. Could look that up, and that gives us 1.42 times 10 to the 6. All right. Definitely not laminar, right? Laminar was 2.3, 2,300, right? So that's, we're way beyond that. So that means we're going to have to use the Moody diagram, which means we also need to know the roughness divided by the diameter. And we are given the roughness, or are we given the material? No, we're given the roughness. 0.16 millimeters for epsilon. So 0.16 millimeters and a 200 millimeter diameter. Don't have to convert to meters because units cancel. That gives us 0.0008. Now, knowing these two, we can go into the Moody diagram, which we have down here. Right, so we can look up our Reynolds number right here. That's our 1.4 times, make that 4 more readable, no, my 4s are not working today. 1.4 times 10 to the 6 would be this line right here. I already put the lines in. And then we can look up here, 008 is this black line, so we just have to see where those two intersect. Well, we're kind of in the area where the coefficient doesn't change very much anymore. So if we go over here, this would be 15, 16, 17, 18, let's say 18.8. Right, so 0.0188. That's what we read off. Let's go back up here. So we can say from Moody diagram, F is equal to 0.0188. All right, now we can go ahead and plug that in. So we can say HL is then, I'll just as a reminder, maybe to write down here, FLD V squared over 2G. So that would be 0. Yeah, probably not going to fit next to there, so let's write it down here. 0.0188. The length of the pipe is 250 meters. 250 meters. Diameter was 0.2 meters. The velocity was 6.366198 meters per second. That's squared. 2 times 9.81 meters per second squared. That gives me 48.54328 meters. That would be my head loss that I get. All right, with that, if we go all the way back up top here somewhere, we have our energy equation. We now have all the terms ready. All right, so let's write our energy equation again. Now with all the terms as they are. All right, so we started with our PA was equal to 0, VA was equal to 0, ZA was equal to 0, and then we have H pump. And then we'd had PB was equal to 0. We calculated what our V was, so V squared over 2G. We said that's the constant everywhere, so we'll just call it V. Then we had ZB, so let's leave that in. ZB. And then we didn't have anything from a turbine, but we have HL. That means we have H pump, that's what we're looking for to get the power, would then be, just like the way it's written there. It's not really so much a this follows, but just a rewrite. ZB plus HL. So all we have to do is plug in some numbers. So that will be again 6.366198 meters per second squared divided by 2 times 981 meters per second squared plus what was ZB was 20 meters. ZB is 20 meters, and then we just calculated what our HL was, 48.54328 meters, and that gives me a total of 70.60895 meters. All right, so that's the pump head. So then we can say the power of the pump, W pump, right, is gamma times Q times H pump. We're not given gamma, so rho times G times Q times H pump, and that is equal to, well, we already said that was 997.1 kilograms per cubic meters times 981 meters per second squared. We said our volumetric flow was 0.2 cubic meters per second, and the H pump 70.60895 meters. All right, so that then means we get 138,133.0 watts, or 138 kilowatts, which is what we're looking for, right? That was the power for the pump. All right, so now we've used the energy equation, and to do that we needed the Darcy-Weisbach equation to get the losses in the pipe, and to find that we needed to use the Moody diagram. But overall we find that we need 138 kilowatts to deliver water from the detention pond to the lake at 12,000 liters per minute.